Well, as the circle, as the sphere gets bigger, the number of gravitons per unit area gets smaller. It gives off a certain number of gravitons, and it gets spread out over a larger and larger surface. What's the surface area of a sphere?
Oh, I don't know. Oh, wait. No. Pi some.
True, there's a pi in there.
Is there a 2 in there?
There's actually a 4 in there.
Oh,
This is the part that matters.
R.
It's a surface area,
R squared.
r squared. So if you think about it in these terms, that the signal gets weaker the more this sphere of gravitons spreads out, r squared. And the 4 pi would get pulled into the G. So this is a generalized formula for the force due to gravity. Making it slightly more formal. The force due to gravity on 1 from 2, so this is force of gravity on object 1 caused by object 2.
Is there anything between the 1 and the 2, or do we just write it like it's 12?
Just writing like a 12. If you want to put a comma in there, there's nothing wrong with a comma. But typically for the subscripts, when you're talking about the 2 different objects, it would be, the comma is usually not written. All right, so we have to somehow indicate direction. I know the magnitude is big G, mass 1, mass 2 over r squared. And to indicate the direction, well, mass 1's getting pulled towards mass 2, towards the center of mass 2. So towards the center of mass 2, the negative up front, and then the r hat, r2 hat indicating, 2 is indicating the center of which r is based. And so that's a more formal presentation of force due to gravity a la Newton.
So why do we put the r hat squared for subscript 2?
The r hat sub 2, r2 sub hat. Because the force on mass 1 is towards the center of mass 2.
So it's just showing that it's that direction.
Yes. Yeah, the negative r2 hat is showing the direction of the force on mass 1.
Okay.
But if we had, for example, if we set up an equation like, or if we set it up like r hat, and then did the parentheses, and then wrote out the equation, then we wouldn't have to put in r hat, would we?
Wait, say that again?
So you know how like when we're setting up previous equations,
Right?
we write out
Oh.
like this?
Yes, so the fact that we didn't write it here?
You're right.
Yeah. All right, let's find out if there's any justification for this. I mean, does it match stuff we've already learned? So let's take a situation which I do know. Earth and me, not to scale. I'm standing on the surface of the Earth. I know what my weight is, mg. My mass is about 100 kilograms. Acceleration of gravity, we'll just go to a generic 9.8 meters per second squared. So my weight's about 980 newtons. I should be able to use the same formula because that's also a force due to gravity. So big G, mass 1, mass 2 over r squared. So big G, that is a constant, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared.
Is that just what it is?
Yeah. Sometimes I go out a few more, that's what I remember, but on tests and so forth, sometimes you'll see a couple more digits there. Mass 1, I'll give myself mass 1, 100 kilograms. Mass 2 would be mass of the Earth, 5.98 times 10 to the 24th kilograms. Over the radius of the Earth, basically it's the distance from center to center. I am assuming that my size is insignificant compared to the Earth. And so therefore, I'm just gonna do the radius of the Earth. 6.38 times 10 to the 6th meters squared. And if someone would be kind enough to crank that out,
Can you say that last number on the end?
this one here, 5.98 times 10 to the 24th.
And then the first number was 6.67 times 10 to the negative 11?
Yes.
Whoa.
Is that just, what does that number represent, that last one?
That's the mass of the Earth.
Okay.
I think whatever it's gonna end up being is going to be a very, 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 very small number.
See? I think it's gonna be somewhere around 980. Is that small? It depends on what you compare.
Relative to whatever we're talking about, yes, this is small.
The answer is
979.9.
units. Somebody just said it.
Newtons?
Yeah. It's a force, it better be newtons, but we can always do a quick check here. That kilogram squared is gonna cancel out with those kilograms, and this meter squared is gonna cancel out with that meter squared. What we're left with is newtons. All right. Which is pretty darn close to that.
Which confirms that what did you just confirm?
That big G works, basically, right?
Say it again?
This confirms that the big G works.
Yes, or it confirms that this formula works, depends on where you want to.
Okay.
There's something that's matching here. If you want to attribute it to black magic, so be it. And in naturalized units, big G has a value of 1. All right. What I want to do is, well, let's figure out what the mass of the sun is. Oh, it does require some information that I don't have off the top of my head. Textbook here. I'm gonna go grab a textbook where I can get some nice numbers. And I'll be right back. I'm just gonna let the video run. All right. Let's figure out what the mass of the sun is. Questions before I erase some of this?
So again, we're just the force. We didn't know little g because it was we had two two objects in space.
Yeah, pretty much.
But if like, yeah, so we had like two planetary sized, you know, things, or one planet, one sun, which it's now on a scale that you need something that is constant among all of the gravities.
You go for like big G?
Yeah.
Yeah. Actually, in terms of what little g is, similar to what we had over there, the force due to gravity, g mass of 1, mass of 2 over the distance squared is equal to m1g. I mean, that would be the formula right there. This would be the mass of the central object. I'll put central in quotation marks because that's a vague term. The other object. And so big G times the mass of the Earth divided by r squared would be the formula for little g. We've taken the mass of the small object out of it. Actually, on this note, suppose I went up 100 kilometers, which I believe is considered the edge of outer space. What's the acceleration due to gravity 100 kilometers off the surface of the Earth? We can figure it out. 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24, divided by R, which would be 6.38 times 10 to the 6th, plus 100 kilometers, which is 1 times 10 to the 5th squared. So if we're on the edge of outer space, what is the acceleration due to gravity? So this down here would be 6.48 times 10 to the 6th squared.
What'd you get the bottom number from again?
It's the radius of the Earth plus the altitude.
And this is given?
I said, so radius of the Earth given, altitude, I said if you're 100 kilometers.
So given.
Yeah. So it's 9.8 here on the surface of the Earth, and then on the edge of outer space, it is we're all trusting in Justin. What'd you get?
39,860.
Yeah, that's not right.
I got 9.498
Units?
meter per second.
Yes. It's really not that much different than it is here, which is our justification for generally considering little g to be constant for all of our free fall problems.
I have a question.
Yes.
How did you get the 6.38 times 10 to the 6th plus 1 times 10 to the 5th?
All right, so
No, to turn into the 6.48 times 10 to the 6th.
good. You understand why I'm adding those?
I understand why you're adding.
Okay. 6.38 times 10 to the 6th, that's 638. So that's that number. The other one, you would move it 5 places and you would end up with 1, 0, 0.
So you just did the math in your head.
Sorry.
You just did the math in your head.
Yeah. Yeah, I thought that's enough time. Or you could also look at it as 1 times 10 to the 5th. If I move the decimal, there's an implied decimal point there. If I move it that way, in order to have the same number, I have to increase that to offset it. So it's also 0.1 times 10 to the 6th. And so now I'm dealing with the same power. All right, questions? Before we figure out the mass of the
Sun.
sun. All right, so we have G, mass of the Earth, mass of the sun over the orbital radius of the Earth equals mass of the Earth, V squared over R. What can I cancel out?
What is that subscript? On the M.
That's M sub E and M sub S. Over here is M sub E.
Oh, the mass of the Earth.
All right, mass of the Earth goes away. I can get rid of one other thing.
R.
Yeah, I've got an R here, and I get rid of one of the R's there. So I'm now left with G, mass of the sun over the orbital radius equals the speed of the Earth squared. Doesn't really help us a whole lot yet, unless you know how fast the Earth is traveling.
How fast is the Earth traveling?
What?
How fast is the Earth?
How would you find it?
You could. Oh, find. You know, it goes that whole circle in 365 days. You would have to split it up. I don't know, but that's how
Oh,
you do
you're
it.
so close to saying all the right things there. I mean, what you said was correct. In general, how do you find speed?
Distance over time.
Yeah. And it's traveling in a circle, so what do we call that distance?
360. No.
The distance.
Uh,
Yes, and the formula for the circumference?
2 pi r.
So 2 pi r divided by how long it takes to go around once, which is the period 365 days, but we'll probably want to put it in seconds.
Yeah.
Unless you want bizarre units. So this would be 2 pi r over t squared. So I've got G, mass of the sun, over r is equal to 4 pi squared r squared over t squared. Just squaring all the stuff in the parentheses there. So from here, we can go several directions, but mass of the sun, which is what we're trying to find, 4 pi squared r cubed over big G t squared. Now, I think most of us can handle everything here except for this r. This is one of the reasons I went to the other room to get the book. That's not what I want. No. It does not have that bit of information.
Okay.
Would someone look up the orbital radius of the Earth? That seems odd.
The radius of the Earth equals 6,400 kilometers, and the radius of the orbit of the Earth about the sun equals 1.5 times 108 kilometers.
Times 10 to the 8th
I think so.
kilometers.
Yeah.
All right. So 1.5 times 10 to the 11th meters.
Is equal to R.
Yes. So this is 4 times pi squared times 1.5 times 10 to the 11th meters divided by 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times the period squared. Now we know it's 365 and a quarter, give or take. Let's see, we'll crank through that math over here. Now, I strongly recommend getting in terms of seconds because there are seconds built into newtons. And so if we did it in years or days, we really have to keep track of units and can't just go with, oh, we're finding a mass, so the answer is kilograms. So 365.25 days. I want to get that into seconds.
Where you put it over the one, you put it over one, makes it be hour?
You want to get it into hours?
Well, you would go from hours to minutes, minutes to,
Okay, so days to hours.
there's 24 hours, you would just do 365, 0.25 times 24 to get how many hours in a year?
Times 0.4.
No.
24.
He said 365.25.
Right.
Times 24.
24.
That's 20, okay. 24 hours per day.
How many?
60 times 24 for minutes.
60 minutes per hour.
And then 60 seconds. I googled it, and Google said approximately 3.154 10 to the 7th.
This, I believe, is 86,400 seconds per day. All right, so we have our time now, assuming Google is not lying to us. So 3.154 times 10 to the 7th seconds.